So now we will see about the structure-activity relationship of the pyridoxine and also the dihydropyridine. So this is the structure of vitamin B6 and also its derivative. So as you can see in here, we have a pyridoxine structure and it has some derivatives. So you can change this hydroxyl group into the phosphate group and also this side with the aldehyde group and it becomes a pyridoxal. And also you can change it this side not into the aldehyde but into the amino groups, and this is used still phosphate group and it become a pyridoxamine 5 phosphate. So this is the structure and we can identify for which reactivity, which part has a good reactivity. We can identify one by one. So for example, in here we take a structure of pyridoxine and we can identify, for example, in here we have a phenolic group. So please be careful, this is a hydroxyl group. If you attach in here is a aliphatic carbon, so this is a hydroxyl group, and this is the hydroxyl group attached with the phenyl ring. So this is the aromatic ring, so it's become a azaphenol. So you can look again for the nomenclature part, and for this part, for the methyl part in here, we have CH acidity. So as you can see, so this is the neighbor atom is a nitrogen, and also it's connected with the aromatic system. So it's more electronegativity, and the distributions of the electron is concentrated in this part. So for this hydrogen, it's become the acidity. It's possible for the hydrogen to be released from this part. So it's make this hydrogen has an acidity. And for this part, for number 6 especially, so actually in this part we have one hydrogen. So if you check, this is only 1, 2, 3. So it's only 3 connected with the neighbor atom. So C in the 6th position still attached to one hydrogen. And in this part, it's the activated position, so you can easily substitute this hydrogen with the other electrophilic group. So it means we can identify this position as an activated position for the substitution electrophilic. And after we identify for each part, so we can identify the reactivity of the pyridoxine. So we have a hydroxyl group at the C3 positions or the azaphenol, and we have for the nitrogen at the first positions, and this is so basic for the properties. And this basicity is making alpha picoline at the C number 2, and in here has an acidity that I explained in the previous slide. And if you have in here another derivatives of the pyridoxines, and you make this nitrogen is alkylated, for example, so you have N plus in here, so it increases the acidity of alpha picoline in here. And then for the C number 6 position, this is open for the electrophilic substitution, and this is also caused by the phenolic group at C3. So if you remember again about the lectures about the electrophilic substitution, especially for the aromatic substitution, so any substituent for the first substituent, it will have an effect at the ortho and para. So as you can see in here, number 6 is the para position with the hydroxyl group in number 3 in here. And also, if you have a pyridoxal, if you still remember for the pyridoxal, in this part you have the aldehyde group. And if you compare or remember in the previous sections, so aldehyde is the one example for the reactive group. So this is the reactive part of the pyridoxine. So after we identify the reactivity site in the structure of the pyridoxine or pyridoxal, so we can see what is the function of the pyridoxal or what is the role of pyridoxal in our body. So because of the pyridoxal has many spot or many reactive site, so it can act as a coenzyme for catalysis of this kind of the reactions, such as a transamination, aldol cleavage, decarboxylation, and also the racemization. And for the process in general, so it consists of the acidity in the early step. It consists of two steps. So the first one is the activations of the alpha carbon atoms in the amino acid. And next is the formation of a C base from the aldehyde group in the pyridoxal phosphate and also the amino group from the alpha amino acid. And this is the structure of the pyridoxine. So pyridoxine has many spots that can be ionized and involved in the ionization process. If it's depends on the environment, it's an acid or base. So this is the basic structure of the pyridoxine. As you can see, for example, we put this pyridoxine in the acid environmental. So if you see, this part is basic and it's already ionizations for the N plus in here if you put it in the acid. But for this part, so this is the phenolic group. So if you still remember, so the properties of the phenolic group is a bit acid. So this is a slightly acid. So if you put in the acid environment, it become a base structure. So this is the base structure for the phenolic group. It's become an OH. So this is the structure that you can find if you put the pyridoxine in the acid form. And now we move. How about the basic condition? So if you put this pyridoxine in the basic form, so it will move the hydrogens attached to this nitrogen. So this nitrogen is actually a basic one, so it will come back into the base structure. So this is the base structure, so it's only nitrogen without the additional of the proton in here. And for the phenolic group, because this is a slightly acid, so if you put in the basic conditions, it will be ionized and it will change into the O minus. And actually this is also the alcohol groups in here is a slightly acid. So if you put it in the strong base, so it can be also ionized, become a O minus. But if you put like a only slightly base, like a pH equals to 8 or 9, so maybe the alcohol group still in the alcohol form. But if you put like a strong base, like maybe sodium hydroxide solution, so you can find this hydroxyl become O minus also. And the pyridoxine is also have some interactions with the drug. So this is the interactions of the pyridoxine with the drug. The first one is the formations of hydrazone with the ENH, And also this hydrazone will inhibit the pyridoxal kinase. And the carboxylations of levodopa into the dopamine that make the effectivity of the therapy will be reduced. So let's see one by one for this kind of interactions. So the first one is the interactions with the ENH or isonicotine hydrazide. So this is the isonicotine hydrazide structure, and also this is the pyridoxal group. So the reactive site is the aldehyde group in here, and also in the ENH, this one is the most reactive part. So this aldehyde group will interact with this one to make a hydrazone. So this is the structure of the hydrazone. So if you can imagine, so this is just a substitution. So this is a CONH. So as you can see in here is the same CONH and it should be a NH2 group for the isonicotine hydrazine. But now the two hydrogen is removed and react with the aldehyde group and attach with this pyridoxal group. So it will be attached with this aromatic system. And this is the hydrazone. And the last one is the interactions with the levodopa. So this is the structure of the levodopa, and this is the pyridoxal phosphate, and this is the reactions. So the levodopa interact with the pyridoxal phosphate, and it will also change the levodopa become a dopamine. So it will remove the COOH group. So this is the react with the dopa decarboxylation. So this is the interaction. So first is the pyridoxal will enter the center of the active site of the dopa decarboxylation, and it will increase the kinetic of the decarboxylation process. So the carboxylation process means the removal of the COOH group. So it will change the levodopa into the dopamine, and also this process is increased if you put or if you add the pyridoxal phosphate. So naturally it also happens, but it's so slow. But if you put it together with the pyridoxal, it will increase the speed of the reactions. And if the levodopa is changed a lot into the dopamine, it will reduce the activity of the levodopa treatment. So next we will see about the derivative of the dihydropyridine. So dihydropyridine has so many compounds. So this is the name of the group, and for the prototype in here we use nifedipine. So this is the structure of nifedipine, and for the nifedipine, you can obtain this compound from the Han synthesis method. And as you can see for the 3D structure, so this is the ring of the dihydropyridine. So if you still remember, so this part is not rigid. So the rigid part is only this ring, and this can be rotate into this position or go to the below position. But this is the conformation or the best conformation or the stable one. So it should be from a shallow boat conformation. And also for this benzene ring. So if you remember, so this is attached with the aliphatic one. So only one bonding, something like this, single bond. So it can be rotate. But the most stable one, if the benzene ring is perpendicular to the both conformation. So this is depends on the conformations. And why is the perpendicular is really the stable one? So this is caused by the nitro group in here. So the nitro group in here is making a steric effect for the substituent in the dihydropyridine in here. So if the benzene ring is perpendicular, so it can minimize the steric effect. So you can imagine if this is not the perpendicular, so it's in the parallel positions. So this nitro group will be in the same position with this kind of substituent. So it will make unfavorable bond or steric effect. And for the nifedipine, it has some reactive site, and it can change the disproportionality intramolecular. So it means like in the previous one, we see the pyridoxal will have interactions with other molecules or other structure, but this is the intramolecular. So intramolecular means like with its structure itself without interact with other structure. So this is the structure of nifedipine in the 2D structure, but this structure is not stable in the exposure of light. So maybe you can observe like some drug or some chemicals. Sometimes it's stated like please avoid to the light or the exposure of sun. Or if you see in the chemicals, so sometimes you must put it in the brown bottle or keep it protected from light. So you give like aluminum foil to protect it or something like that. So this is the example. So if you see if this compound is exposed by the light, so it can be making some reactions inside of its molecule. So without react with other molecules, so this will be reduced from the nitro group into the nitro monoxide. So this is the name is the 4,2-nitrosophenylpyridine. So this is the structure. And if this nifedipine already changed into this structure, so this is no effect. So if you consume this drug and then you expose the drug with the light, and the drug is already changed into this nitro monoxide group instead of the nitro group in here, so you will got no effect. So this is the example of the disproportionality intramolecular.